Everybody. I am Subhadeep Ghosh. I work at ProMiles as a developer for Astroware Bridge Design and Rating. Today, I would like to talk about Astroware Bridge Design and Rating 3D FEM analysis capabilities and troubleshooting. Um, Astroware BrDR capabilities include uh, 3D modeling of straight multi-girder system bridges, which includes steel beams, which has steel beams and reinforced concrete beams uh, as I's and T's, or pre-stressed concrete beams as I's, T's, or boxes. Uh, Astroware BRDR also allows modeling of curved multi-girder system bridges, which contains steel beams. The modeling is primarily done with beam elements and shell elements. So when we talk about beam elements, the beam elements considers it's a Timoshenko beam element, which considers shear deformation and or rather shear effect and rotational bending effects. When we talk about shell elements, it's a 4-node shell element with 6 degrees of freedom at each node. It has a lock-free formulation for thick and thin shells, as well as the shells would not lock when they are thin shells, and also the shear deformations are captured for the shell elements used. Coming to reinforced concrete beam modeling for girder system superstructures, which has reinforced concrete beams, we have two different models. We have a stage 1 model and we have a stage 3 model. For stage 1 model, we have beam elements with moment of inertia and cross-sectional area, and the beam elements contain the section properties for the beam as well as the top flange or the deck. The stage 3 models, the girder, web, and the bottom flange are modeled as or beam elements, and the top flange or the slabs are modeled as shell elements. The beam and the shell element and the beam elements are connected to each other via the master-slave constraint, where the node at the girder level is the master, and the node at the deck level is at the deck level is a slave node. So the node which is at the deck level is at the half thickness of the deck, and there is a schematic which shows a modeling of a typical reinforced concrete section where the beam element for the beam section for the web and the bottom flange, if applicable, is at the CG of the beam, and the deck or the top flange is at the half depth of the deck on the top flange. Pre-stressed concrete beam modeling, we have three models here. The stage 1 model is a non-composite section model where the beam element is used for stage 1 modeling. So beam element where the I's and the A's are considered only for the beam section, and the stage 2 and stage 3 models, which are composite models if indicated by the user in their model input, and they consider the stage 2 and the stage 3 model consider the girder as beam elements and the deck slab as shell elements. Again, similar to reinforced concrete slab system, the deck and the beam or the girder are connected to each other via the master slave constraint, where the girder nodes is the master node and the deck node is a shell slave node. Again, a very similar schematic is shown here for how the cross section is modeled for a pre-stressed concrete beam when it is part of a girder system for 3D modeling. Moving on to steel beam modeling, it's a little more complicated, where the stage 1 model, we have the top flange and the bottom flange. The flanges are modeled as beam element, whereas the webs are modeled as shell element. And for the stage 2 and stage 3 model, it's a composite section model. Again, the composite section is based on the user defined components in the model itself. And the flanges are modeled as beam element, web and the deck are modeled as shell element. Similar to the previous two modeling, we have a master slave constraint here between the top flange and the deck node, where the deck node is connected to the top flange node via a master slave constraint, where top flange node is the master and the deck node is a slave. This schematic shows a representation of the modeling of the cross section, where you can see the web is divided into three parts by shell elements, and we have beam elements for top flange and bottom flange, and then we have the deck shell elements on the top, which is connected to the top flange beam element via the master slave constraint. We also have in steel beam modeling for three-dimensional for 3D FEM. We also have cross frames, which are modeled as a beam or truss element based on the end conditions entered by the user in the cross frame definition window. We also have a curve modeling for steel girders, where we use small straight elements uh, to model the curve beam, and with small kinks at node points. The curve elements are not used for modeling curve bridges. This is a sample window. This is a window which shows the user input for a diaphragm definition, which is gets assigned in the framing plan window, and the diaphragm definition controls how a certain cross frame or diaphragm is modeled for 3D FEM. The uh, the support type defines the end condition for the diaphragms, and and this input here defines where the diaphragm is attached to the web, or to the web of the girder. These are the different shapes of diaphragms that are allowed in BrDR. Uh, all the shapes are allowed for a steel diaphragms, like all from type 1 to type 4. Only type 4 is allowed for concrete diaphragms. Uh, we do spec checking of all types of diaphragms except for a type 4 diaphragm when it is made of a concrete material. So diaphragm after the dead load analysis of a diaphragm and a live load analysis of a diaphragm member, we also do diaphragm spec checking, just like a girder spec checking. We do diaphragm spec checking, and so this window, I would go back one slide. This window shows the connection information of a diaphragm for each member, and these connections are not modeled in the finite element model, but these connections are entered for spec checking by using the member forces. So for example, we have the work point offset for a bolted connection member, which impacts the calculation of the slenderness ratio. We also have input for bolt lines, which can be used for spec checking the connection for the diaphragms or the diaphragm members. We also have bottom flange lateral bracing, which can be modeled into the 3D model, and it can also be spec checked. Coming to analysis control options, like I spoke in the beginning, that based on the user input, uh, you can model the 3D bridge as a composite model or a non-composite model. So if you wish to model the beam, or the beam, I would say, as a non-composite model, you can use this 3D analysis control option here. In this case, in this scenario, if you check these boxes, and for regions where you do not have, say for example, for a steel beam, you do not have, for the negative bending region, you do not have your shear studs defined, you want to model the negative bending region as a non-composite region, you have to check this box. And what this will do is, for that non-composite region, it will model the master slave constraint only with a vertical displacement constraint, and it will not use any other constraint for master slave. Another analysis control option is this, which is stated in LRFD 6.13.1 article. This is related to primary members like, uh, or rather, primary member connections and splices. This is mainly implemented for, say, for diaphragms where we spec check the connections. So based on the selection here, we will either use the calculated factored member force effects as design force or design force effects, or we will use the maximum of average stress plus strength or and the 75% resistance of that member. Coming to mesh generation and user control, the BrDR generates mesh automatically on the finite element model by using certain user controls that the user provides, which the user controls are generally based on what the user enters on each member. And so as you can see from the slide, it says nodes are always created at 10 points, section change points, diaphragm, bottom flange lateral brace points, supports, and user-defined points of interest. Uh, the Also the node creation is also dependent on what you enter on the snapshot of a input that is shown on the right hand side. So the first input says in deck between girders, and the second one is in the web between flanges. Now, and the second input is target aspect ratio for shell elements. Now the first one in the deck between girders is applicable to all types of all types of bridges like reinforced concrete pre-stress as well as steel. And if this is entered, then what happens is this determines how many shell elements will be used between girders in the deck. And then for the web, it will be using the aspect ratio used in the used for deck shell element modeling to model the shell elements in the web. And but there is also a minimum limit for number of shell elements that are allowed in a web. So that number is 2. So you can the minimum number of elements in the shell in the web that we can go is 2 for shell elements. Also keep in mind that this number of shell elements between girders or number of web or number of shell elements between in the webs between flanges impacts the degree of freedom of the analysis. That can greatly impact the speed of the analysis. If you select in the web between flanges for number of shell elements, the same thing will happen where it will determine the length of the element based on the aspect ratio, and then based on that it will add the, the elements in the deck between the girders. So this is a quick example, which this is an isometric view of a 3D model, and this is modeled using the first radio button in deck between girders for a steel beam superstructure, and these arrows shows the number of deck elements or number of shell elements between girders that are added, and then based on that we add 2 shell elements which has the same length as the based on the aspect ratio as the deck elements or the shell elements between girders. Another process in the another mesh generation process we follow is the we in order to build a model or in order to mesh the model, we use a nomenclature of we use same number of nodes along each girder. We also maintain equal number of nodes per span for each girder, and we also keep the nodes at the same percentage for each span length. So this is an example where it shows where for the girder G1 we have an user-entered plate which changes at 76% of G1 in span 1. And then for G2, we have user-entered plate which changes at G2 at span 1 at 75%. So, so to go to the previous rule, we have to create the same node on the other girder, which does not exist for that girder. So for G1, we add another node with at 75%, and for G2, we add another node at 76% due to the presence of that same node on the corresponding girder at the same percentage. These nodes are generally marked with a bit mask 0, and we will talk about troubleshooting, and we'll come back to how that bit mask will help you out when you're modeling a 3D model. Support conditions. So if none of the supports are fixed, they are generally the bottommost node of the support, or the bottommost node under the beam element is generally supported. Everything above that is generally free. So, but if the support is designated as fixed, then all the vertical nodes are constrained for translation. For rotation, X is never constrained. Rotation Y is constrained just for beam elements, and rotation Z is constrained for all the nodes. So the schematic here on the right-hand side shows a simple example of a fixed steel support, a steel support which has been designated as fixed, where you can see that a support has been added at all the edge nodes for a fixed support. For curve support conditions, where you can define bearing constraints in the local coordinate system at each support. So you can either define the bearing as or the bearing constraint along the tangent of the member at the support location, or you can define a chord angle. You can define a chord at a certain angle to the tangent for that support. You can also define you can also define an incline constraint. I mean, this can be used to define an incline constraint where a line is drawn perpendicular to your support direction uh, to restrict the movement of the support in that direction. And then, as you see in the schematic here, the support is only allowed to move along the local x-axis of this support. Okay, so after we are done with the 3D analysis, we have the shell element, we have the beam element, and but we need to our end goal is to to do a spec checking on the model, or do a rating on the model, or do an LRFD design review on the model. So what happens is, after the 3D analysis is done, we have to transform the 3D analysis moment from a 3D moment to a 2D moment. So this schematic shows how we transform from a 3D moment to 2D moment, where all the components of the cross section is taken, the forces from all the components of the cross section is taken, and the moment is taken about a point of the cross section to generate the moment for a 2D analysis. And then that 2D analysis is that 2D moment is transformed, or rather applied to a equivalent 2D model, or 2D model, which is used for spec checking of that model. This way of transforming moments happens both for the dead load analysis as well as for a live load analysis. Uh, I would like to mention just another point here is, for live load analysis, uh, a direct transformation happens from a 2D moment to a 3D moment. But for dead load analysis, a direct transformation happens from a 2D moment to a 3D moment to a 2D moment. But for a live load analysis, we generate the influence surface by applying unit loads on the deck, and we generate influence surface for each node on the girder, and we figure out the worst case scenario for certain actions, and then from that worst case scenario, we generate the 2D moment for that section. Specification checking for a 3D FEM analysis, ASD is not supported. I would say we say ASD or ASR is not supported. LFD or LFR in specification terminology. We support straight steel, pre-stressed reinforced concrete. We support AASHTO standard specifications. For curved, we support AASHTO guide specifications for horizontally curved steel girder highway bridges. And for LRFR, we support MB specifications, as well as for LRFD, we support LRFD specification checking for design review. Okay, so now we come to troubleshooting different analysis problems. You may have had problems where your analysis is running, your analysis is probably running for a long time, or you're running out of RAM space, or you're running out of hard drive space, or just it's stuck at a point and it doesn't seem to move from that point. So we have some general tips as to how to troubleshoot these scenarios. So we generally recommend a 64-bit using a 64-bit BrDR. Now this was more applicable when we used to release a 32-bit BrDR back in the day. I'm not going to say back in the day, a couple of years back. But with 64-bit BrDR allows you to have more memory when you do the analysis. Also, we recommend using an i7 processor or an equivalent. We recommend using a RAM, a 32 GB of RAM. We also recommend that if you cannot increase your RAM, you can probably talk to your IT and work with your virtual memory to provide more memory space when you are running an analysis. And we all definitely recommend having a solid state drive, a drive to which all your output files are getting dumped into. So analysis speed is primarily dependent on the number of degrees of freedom you have in the model, which, as I've shown before, you can control the number of degrees of freedom that you have in the model. It is controlled by the number of lane you generate on the travel way, or the live loading increments you have, the number of live loads you're analyzing, and where you are outputting your analysis output files. So let's talk about the degree of freedom. We just talked about the degree of freedom, or this window where you select how many shells you want between decks and how many shells you want between in the webs between flanges. Also sometimes due to a higher aspect ratio or lower aspect ratio, we had few points where we generate POIs for modeling, but for certain aspect ratio, to meet the aspect ratio, we also add extra points to the model, so which can make the model much more refined. So degrees of freedom is one of the major component of controlling analysis speed. You may have seen when you're running an analysis, it would say computing transverse lane positions, and it gets stuck there for days. And you have questions for our support that it is stuck at this point. How do I get the analysis to move? And it's not doing anything. So you can actually control that scenario. Like you can define how many or especially for this transverse loading, you can define how many lanes you want in your superstructure, and you can control the lane increment in your for your travel way. You can also control the lane increment for a vehicle in a lane in the travel way, and you can also control the longitudinal. So the second part of this screenshot deals with computing transverse lane positions, where you control the number of lanes in the travel way, and also you control the vehicle position inside the travel way. And for the first part, the longitudinal loading, the vehicle increment, you control the time taken for an influence surface generation or influence surface computation. So for every member that you analyze inside a 3D model, it does influence surface loading for like main primary members like girders, or like for secondary members for a straight girder like straight bridge like diaphragms, where it does influence surface loading for all of them. And this longitudinal loading uh, increment or vehicle increment will control that. Another tip is to redirect, not never to direct your output to a network drive, which says on the left hand side, where you can select if you want to put your analysis output to a network drive. So always try to output your files to a local directory. Uh, and also on the right hand side, it'll be a good idea like to uncheck some of the outputs. And the primary one that can take up a lot of time, analysis time, is this LL influence line FE actions. Uh, so if you're not really digging deep into analyzing all the files, if you want a quick analysis, then you will. It's better to uncheck this output whereas your analysis will run faster. Another point is when you're making a big 3D model, you are entering a lot of data inside the model, and you are trying to optimize your model based on the plans and everything else. So it's better to fine tune your model by running a dead load only analysis. So this is a picture of the analysis settings window where for a 3D finite element analysis, you can pick a dead load only analysis. So once you run the dead load only analysis, especially for steel, you can always open up the 3D graphics model viewer and check if your model looks right as per your plans. I would say model looks correct. Also to do a sanity check for the model, you can look at the moment plots for dead load, and 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 even before you run a live load analysis, you can check if all your supports are in the right positions, and your dead load plot looks okay. Also use a coarser mesh initially, which will let your analysis run faster. Coarser mesh also means lower degrees of freedom, so your analysis will run faster. Also, if you also you can focus your analysis on maybe one member, and you can uncheck the existing box for any member that you want to skip when you try to optimize your model or when you try to check your model. So uncheck the existing and just focus on one member to check whether the analysis results look right or not. You can also avoid spec checking the diaphragms when you run the analysis for the first time. You can spec checking all these boxes for diaphragms will do influence surface loading for those diaphragms and also do spec checking for those diaphragms. So when you're trying to make sure that you're or fine tune your model, you can uncheck these boxes and it will make your model run faster. Unchecking these boxes for diaphragms will still give you a diaphragm a dead load action. Okay, when you're evaluating zero end moments, you can work with the support conditions to troubleshoot, or rather, when you see non-zero end moments and you see you can mess with the support conditions to see if it makes your model better. Okay, you may have seen different number of node. You may have seen this error messages when you are trying to work with a 3D model. All members not have the same number of nodes. Model cannot be generated. So there is a file that outputs a location of all the nodes on that member, and that file name is called 3dgirder nodes.txt file, and it has all the nodes, and it also has a reason why that node was added. In the older versions in 683, that file used to be generated only when we would have this problem, but for 684 and like for 7.0, this file will always be generated. So like I mentioned before, the node generations are for diaphragm support 10 point cross section change points, and then you'll see something called a bit mask 0 for a node presence reasoning, which is generally added for the same number of nodes in the span, to maintain the same number of nodes in the span, or because of the target aspect ratio you have defined in the superstructure definition window under analysis tab. So this is a sample of the file that gets generated, and above here it gives you kind of the relative file location where the file gets generated. So what you can do is you can import this file into a spreadsheet. It's a comma separated file. It's a CSV file, so you can easily import it into a spreadsheet. And here is an example of a scenario where G9 has 117 nodes and G10 has 118 nodes. So we'll quickly go over a scenario here where we will examine that why we have a difference in number of nodes. So in here we have on the left hand side we have a span count of 29 nodes. On the right hand side we have span count of 30 nodes. Now if we look at between left and right, we have on the left we have the nodes all approximately the same percentage, and then we again have nodes approximately the same percentage, and then on the left hand side we have a node at 100%, but on the right hand side we have a node at 99.89%. Now to figure out why we have that node at 99.89%, and as you can see there is the node at 100% is right underneath that, so which tells us that a node at 99.89% for girder G10 was added because we have a diaphragm location at that particular point. So what to so so this kind of illustrates why the node got added, and we see that that extra node is for a diaphragm location. So to fix this problem, this is probably for a reason where a diaphragm is very close to a support location. To fix this problem, what we'll do is we'll go to framing plan window where we see that a diaphragm is located at for the second row, a diaphragm is located at 70.53 feet from support to, and then you have diaphragm which is at we have number of diaphragms defined, like 15 diaphragms defined, which is at a right length distance of 258.02 right here, 259.01. So this is causing the extra diaphragm node to be added on the girder G10, which is a right girder. So what we'll do is in order to make sure that the diaphragm is at the same location as the support, we will change the diaphragm number of diaphragms for that row to 14. Remember the last for that row, which was a problem, the number of diaphragms or the number of spaces was 15. So the number of diaphragm was 16. So we will reduce that to 14, and then we will add another row in this grid at the support, and then we will add the last diaphragm at the support. This will ensure that the extra point that we had right beside the support will be at the support location. And this will fix our model.